it's my pleasure to introduce Professor Bulgac, Aurel Bulgac. I have a very short bio here. He has PhD in 1977 in Leningrad Nuclear Physics Institute in Gachina, in former USSR. He has moved a lot, but he has went to University of Pennsylvania, then in Michigan State University as an assistant professor in the 1988 to 1993, and then moved on to University of Washington, where he's now a professor since 2003. He has worked on many things from cold atoms, condensed matter, DFT. You are going to hear a lot about DFT for nuclear physics and fission. So if you want to add something to your resume, please do.
Probably I'll be very brief. Thank you. It's really great to be here. Thank you for having me. This is the second time I'm here. I've been the first time in 2017, and that was relatively shortly after we produced our first major results in nuclear fission in 2016. But over my entire career, I've been studying three-body system. Basically, I was the only student of Efimov, if you know about Efimov effect, three-body, it's a famous thing. I work in cold atoms, molecular dynamics, quantum Monte Carlo, DFT, and probably I forget a few other things. But I published in FISREF A, B, C, D, and E, including PRL and so on. So anyway, that's who I am. So I'll be talking about nuclear fission. So how I started to do this in 2007. And at the time, you see, I want to ask myself the question, can one really apply pure quantum mechanics without any assumption and presumptions and approximation and see a real nucleus starting from a compact size and split into two? And one main reason for that was the emergence of supercomputers, because as you'll see, without that, you cannot really do it. And it took a while. In 2015, we achieved that at last, and one reason was we had to test the code, we had to apply it to other systems to make sure that the method we are using is working, and ever since I'm still learning about nuclear fission. So, as I said, you see, I did that, and I repeat here, but I want to add, you see that little quote there. Never be afraid to try something new. It's what I did. It was totally new for me. Remember that amateurs build the Ark and professionals build the Titanic. So here it is. Yeah. Okay, so nuclear fission was observed in, I don't know, it's something happening here with my, okay, now it's working. It was mentioned a few times by Han and Hans Strassmann. So one thing in my talk, you see, overall, I put in bold phases Nobel laureates. So you'll see many of them. I think it's very important to mark the achievements. And they submitted their paper December 22nd, wrote a letter to Lise Meitner. And in January 16, they submitted their paper, which was published in February. The other paper was published in January. So you look at the sequence there, how very fast it was published. The name fission comes from biology. And at that time, people didn't believe that nuclear fission is possible because everybody had in mind gamma tunneling process. And if you apply that, you'll obtain a fission time something like 10 to 500 years, which was impossible. It's much larger than the life of the universe, or anything you can think. And when Frisch told Niels Bohr was basically in the port boarding the ship to go to US, Bohr said, "Oh, what idiots we have been." You see? So, because everything was much simpler. Now, I'm going to describe what's necessary ingredients in order to describe fission. And one reason why it took so long is because nuclear fission is a highly non-equilibrium process. Now, I'm going to illustrate that for you, why that happens. So, what are the important developments which allowed us to do that? In theory, was the formulation of density functional theory. And I'm going to explain a little bit about this, what it is. And that was due to Kohn and Sham, which proposed it in 1964. And here I forgot to highlight Kohn, Nobel Prize for that. You'll see it later. Unlike all phenomenological model, you see quantum many-body framework should be general for any system, not for nuclear systems only. So if you apply a quantum method, it should work for anything else. And this is the reason in the gap from 2007 and 2015 it took us in order to do fission. So we needed high-performance computing, and we need to implement this on computer. And we used a sequence of supercomputers starting from Jaguar, Titan, Summit, Frontier, Sierra, Lassen, Peace Danes, BAM, and so on. Now, when you do this, as I'll show, you'll have to solve an enormous amount of partial differential equation. They are nonlinear, complex, 3D, time-dependent. We, at the moment, solve up to 5 million of them simultaneously. And it's a relatively simple thing to do. It requires us a few hours, you see, basically. So it's not something which is hard to do, but now it's easy. But it wasn't possible, you see, 20 years ago. Now, I believe that our chance to describe nuclear fission is a pure quantum approach. The reason for that is phenomenological models are helpful, but it could be a minefield. They have unchecked assumptions, uncontrolled approximations, many fitting parameters. And to mention that, you see here it's a quote from Dyson published in Nature. It was a discussion between von Neumann and Fermi. With 4 parameters, I can fit an elephant. With the 5th, I can make him wiggle his trunk. Now count your parameters and find out what he can do. Myself, I need 8, maybe 9, I'll tell you. Now, a great example of this is Niels Bohr paper in 1913, for which he got a Nobel Prize. The conclusion of that paper is here highlighted in italics. You see, and the angular momentum of the electron around the nucleus is equal to h over 2 pi. Obviously, this is wrong. And actually, the next wrong thing, all excited states he predicted have n equal to L. And you know what it's n and L in the atom, hydrogen atom. Obviously, this is what you do when you don't have a theory. And that was corrected later on by Born, Heisenberg, Schrödinger, Dirac, Pauli, and so on. So let's go further. Why we cannot solve the Schrödinger equation? This is the reason why I'm going to talk about density functional. Let's assume that we have plutonium-240, 240 nucleons. Let's assume I have how many coordinates? 720 spatial coordinates. I forget about the spin for the moment. And I'll take 10 points in each direction. How many points I'll need? 10 to the power 720. Do you know how many particles are in the universe? 10 to the 90. Okay, so this is that number. This is significantly bigger than Google. So definitely a computer like that, at least a regular computer like we have today, is not going to do that. Maybe quantum computers will solve this, but I believe that quantum computer will be more like a box, very similar to AI. We put some input, we have some output, but we don't know anything which is happening in between. And that's not only that. We need a different framework. Many reasons for that. That framework has to be clearly formulated, validated, verified, and implemented. Our knowledge of interaction between nucleons is not good enough. I don't have to convince you of that. For example, if you think of the best two-body interaction, which is used in nuclear structure calculation, called ab initio. Do you know how many parameters are there? 21. This is only for the two-body interactions. And they describe that interaction over a certain energy region, up to about 200 or 300 MeV, which is definitely not enough. Nuclei are very dense systems. You know that the average separation between two nucleons is 1.84 Fermi. And at the same time, if you add the two radii of two nucleons, it's 1.75 Fermi. do you imagine, you see how the mean field independent particle motion works? It's like having a box, putting apple in it, and then apple can move freely around each other. They cannot do that. So why? That's the quantum mechanics. So basically, this is one problem you have to deal with. You see, so you have to understand why nuclei you can describe, you see, the way we do. Now, and the other thing which is very important, fission dynamics is a highly non-equilibrium process. And also there is another thing which we discovered relatively recently. It's a non-Markovian process. And it means it has memory effects. Now, here you have a list which I want to summarize. At the end of 1938, when nuclear fission was discovered, what did we know, especially from the point of view of quantum mechanics? And he's highlighted everything we knew at the time. And as I said before, you see, I put the names in boldface, you see, to know the contribution, you see, to all that. And that wasn't enough yet. So we knew about the quanta, we knew about the superconductivity, but not the theory of that, which required another 51 years. We knew nuclear sizes, and Rutherford was an absolutely remarkable fellow. His mentee postdocs, 12 of them got Nobel Prizes, and many of them are listed here, you see. So now, nuclear physics contributes a lot, you see, and you see here names. And we knew about the range of nuclear interaction since 1930s. We knew about the Pauli principle relatively soon after that. We knew about the spin of the fermions at about 1930 or so. Now, we knew about the quantum mechanics in the end of 20s. And in 1936, Hans Bethe wrote 3 long review modern physics, altogether 400 pages, 540 pages, I'm sorry, which is often called Bethe's Bible. You should read that and find out, you see, how much insight he had, even though people knew very little. Now, at that time, the method Hartree-Fock was introduced, you see, in the 1927, I believe. Now, we had contribution to the leaky drop model for fission coming from these people, starting from Gamow, Weizsäcker, Bethe, Bohr, Meitner, Frisch. And the rest is here already mentioned, but I want here to make a note. Lise Meitner was nominated for Nobel Prize 49 times. I think it's something absolutely impressive. She should have got 2 Nobel Prizes. She discovered the Auger effect a year before Auger, who got the Nobel Prize for that. Okay, let's go further. What happened next after 1938? Well, 1939 is the famous paper of Bohr and Wheeler, where they presented a very detailed picture of the leaky drop fissioning, but that came already from Lise Meitner. Inspired by efforts led by, after Schrödinger formulated his equation, 1926, I believe. So inspired by efforts of chemists, John Wheeler proposed a method which was called generator coordinate method, which was based on that. In 1950, Maria Gopper-Mayer, together with Hansen and his collaborator, discovered the spin orbit. The spin orbit in atoms was much weaker than in nuclei and had the opposite sign. And this was baffled everybody. At one time, she gave a talk at the University of Chicago, and Fermi said, "What about the spin orbit?" And that was the result, you see, which she included in her 4-page, I don't remember, it's 4-page or 2 pages letter, which is Nobel Prize. Simply put the spin orbit interaction, change the sign, fit a parameter, and find magic nuclei. Now, in '59, Bohr, Motteson, and Pines, following the efforts of Bardeen, Cooper, and Schrieffer, applied pairing correlation to nuclei. Now, in 1966, Strutinsky made a breakthrough discovery of the magic number can appear in deformed nuclei, a very large deformation. So this is absolutely essential in fission. Now, the next element, and this will be part of what I'm going to talk, and people don't talk very often about this, is that pairing correlation, absolutely crucial, and why George Burst described that in 1980. Now, there was a considerable effort started in 1960, and you look in textbook on nuclear physics, adiabatic time-dependent Hartree-Fock theory, imaginary time-dependent, so on. And basically, they are not used anymore. Now, what's the fission mechanism? How fission fragments are formed, how their properties appear, and what are the crucial aspects of microscopic theory of fission is expected to have and desired to be predictive as opposed to post-predictive. In whatever you'll see now, I don't try to fit any experiment. I put what I know from nuclear physics and see if I can obtain fission and how it looks like. And that's the thing which I'm going to follow. Now, the fission configuration, so what Lise Meitner noticed and Fresh, that if you have a nucleus and deform, the volume stays the same because that's the property of nuclear matter. But at the same time, the surface of the nucleus changes. And that what tells you that you have a surface tension and the energy of the nucleus increases. And this is what you see initially when you deform. But at the same time, you separate the electric charges further and further apart, so the Coulomb repulsion goes down. And that's the reason why eventually the two effects, Coulomb repulsion and surface tension, they equilibrate at this point. It's called saddle point. And after that, Coulomb repulsion gains and basically have fission. Now, another thing which is very important that was noticed by Algebord in '56, and several people mentioned that if you look at the nucleus at the top of the barrier, fission barrier here, and which it's created by absorbing a nucleon, which induced very low energy nucleon absorbed by the nucleus. Eventually, from the ground state, the nucleus is here, evolves by deforming the shape up to here. But here, basically, it's in ground state in that enclosed chamber because he has a given shape. But it's in the lowest energy possible state. So basically, it's cold. Here, it was relatively hot. The excitation energy is around 5-7 MeV, but here the excitation energy is less than 1 MeV. So it's very, very cold. So you start with a very cold system, basically in the ground state, and that will go down this slope. Now imagine that you're in the mountains. If you have skis, you'll go extremely fast down the hill. Now if you don't have them, you'll go very slowly. Exactly like having a parachute. You'll attain a terminal velocity, and you'll move with that velocity until the decision point. So that's the reason, that's the main difference why nuclear fission actually is dissipative, because you have strong dissipative forces which force you to move with very small speed. And I'm going to show you why. Now, there are a few aspects which are surprising about fission. The initial nucleus, it's in the ground state. You have a low energy neutron with very low momentum, angular momentum. Total momentum, angular momentum of the compound system is very low, of the order of 1 at most. At the end, you have two fission fragments which rotate extremely fast. They are very hot, while the initial one was cold and didn't rotate. This is what you have. So you have to explain that. Now, I want to stress that even though many authors have used the term microscopic, there does not exist yet a full microscopic theory of fission. And I'll come to tell you about why density function is still not the ultimate step in that direction. Only partial microscopic approach have been used so far, and I'm not talking about phenomenological models. I'm talking about those papers where they put microscopic in their title or their abstract. Okay, and how fission was described until now. There were quantum frameworks, which they pretend to be microscopic, generative coordinate method, shell model, Hartree-Fock approximation, Bardeen-Cooper-Schrieffer extending to nuclei, Hartree-Fock-Bogoliubov approximation, Born-Oppenheimer approximation. I don't know if you remember, you see, since we're in this place where Oppenheimer was so influential. And I think in late 1920s, he went to Germany and wrote a paper, now I forgot, with Sommerfeld, I think, on Born-Oppenheimer approximation. You have two molecules surrounded by electrons, and the molecules, the nuclei move extremely slowly, the electrons move very fast, and that was the adiabatic approximation. But they didn't include only the lowest potential energy surface. They included some others because you have non-adiabatic motion. But what people in nuclear physics did most of the time, they took only the lowest potential energy surface. Now, there are statistical models which, to some extent, you see, they have classical features, and they in particular ignore entanglement interference, and I'm going to talk about that towards the end of my lecture. There are semi-classical or classical models, and I'm not going to talk much about this. Briefly, basically I want to tell you what density functional theory is. And it's an important, a very important point. It has to be extended to superfluid systems. What is important in this sequence, you have to prove that mathematically the two approaches to describe quantum many-body system, they're identical, at least in some respects. If they are not identical, then you don't know what you're doing. Now, the density functional theory depends on an essential element which is called energy density functional. And this is similar to what you have in classical mechanics, Lagrangian density, to construct the classical action. You have an integral over time of that and so on, you do that. Now, can you derive the energy density function from the Schrödinger equation? Not really. Now, you have to ask questions which are absolutely crucial. How good is time-dependent DFT, density functional theory, for fission? Is it good enough? No. And I'll tell you why not. But it clarified a lot of questions. Now, let me go further. Can one practically show the equivalence of the two? You see, there is an answer to that question, and I think I'm going to go to the next slide here. You see, density functional was invented by Kohn and Hagenberg in 1964, and this is the number of citation to that paper. You see, it's about a month ago or so. Now, a year later, they wrote another paper, and this is the number of citation to that paper. This is the entire foundation of density functional theory. What did they do there? They basically prove mathematically that if you look at the number density alone, and you look in density functional theory, what that is, and then you look in Schrödinger description, they are identical. They give you exactly the same answer. The problem with the Schrödinger equation, you have to solve, in case of plutonium, the Schrödinger equation for 240 particles. Now, for density functional theory, you have to solve the system for the density distribution. And density distribution is a three-dimensional function, depends on three coordinates, not 720. That's the difference. It's a bit more complicated than that. Now, there is another problem. What they did, Kohn and Sham, they did for the ground state of the systems. That was extended for excited states, and in particular time-dependent states, and the same result was shown, that if you look at the density distribution alone in the two theories, they are mathematically identical. This is a mathematical result. It's not an assumption. It's a mathematical proof to this. That's the reason they got a Nobel Prize for that. There is a problem with that approach. Mostly, you see, those citations come from condensed matter physics, particularly molecular physics and so on, where systems are normal, but superfluid systems are not normal. They're superfluid. And unfortunately, not many people study those in comparison with the rest of them. And you have to extend that to superfluid system. The first extension was done in 1988. So you see the gap, more than 20 years here, by Kohn with Gross, who was a postdoc of Kohn at one time. And they published a paper. And unfortunately, this formulation, it's technically very cumbersome. And basically, it's very hard to use. And we developed it, a better formulation of this. Now, let me explain what it is. You want to solve the Schrödinger equation. You have kinetic energy, you have two-body interaction, three-body interaction, you can have any other interaction you can think of, and you might have an external potential. You put the system in a trap, or you put it in a room if you want, okay? And then the question is, you want to solve the Schrödinger equation. This is the Schrödinger equation. Now, Kohn and Homberg proven the following theorem. If you know the wave function, it's easy to derive the number distribution. You take the square of the wave function, integrate of n minus 1 coordinate, one of them you leave free, and you obtain the density distribution. But what they proved was the following. Not that you know this, you obtain that. That if you know this object, which depends on 3 coordinates, and this is a mathematical theorem, you reproduce this function, which depends on 3n coordinates. And this is absolutely nuts. I don't know if you can agree with that. You see, but in case of Schrödinger equation, it's absolutely true. Now, if this is true, it means that this function is completely determined by the density distribution alone, nothing else. But if this is true, you stick this in the expectation value of the energy, and the energy is completely determined by the energy density distribution. Mathematical theorem, nothing else. This is density function theory. The problem is that we don't know in practice how to construct this object knowing the density. You see, this is the problem. But we have an idea how this functional looks like. For example, Kohn and Sham wrote that it should have this structure. In nuclear physics, this should be familiar. This is the kinetic energy density, and you might have an effective mass. Then you have the interaction, like the density square, density cube, coming from 3-body interaction, spin orbit, or some other terms, and so on. And you might put your nucleus in a room. And then you find out, you see how the properties of the nucleus depends on the size of the room. That's your external potential. Now, this density, at that point, they said, we are going to construct from single particle orbitals. So now, from here to here, you see here you had only one function of 3 coordinates. Now you have n function of 3 coordinates, and they could be complex. So that's the complication. But it's still a very simple problem to solve. This is the important thing. Now, what you are going to do in case of nuclei, especially when you want to look at time-dependent phenomena. For the moment, I'm not going to put the spin degrees of freedom or isospin degrees of freedom. The energy density function in that case depends on the density, which could be time-dependent, kinetic energy density, anomalous density, because nuclei are superfluid, and especially because the system is in motion, you have currents, so you need that too. So this is your energy density functional. And you might have an external probe, you see, which pokes at your nucleus. And then you have to find the single particle orbitals, which in this case become Hartree-Fock, Bogolyubov quasi-particle. And you have to solve a system of partial differential equation. It looks like this. This part is exactly like Hartree-Fock. This is pairing field, nothing else. The only problem is that this I symbol here, which in the case of simple Hartree-Fock, it goes from 1 to n, the number of particles. In this case, it's actually, this is continuum. It's 3D. But do you know how to calculate 3D integrals? I think everyone in this room can calculate a three-dimensional integrals if it converges. So that's not a problem. It's only a problem that you have many things, but everything is calculable. So now, how are we going to find the density functional? Since density functional is not an approximation, you have to prove that if you have two equivalent descriptions, they provide the same solution. Moreover, they describe both nature correctly. You see, the fact that two mathematical systems are identical is not enough. They have to describe nature. Next step, you have to implement it numerically. And you see the implementation is complicated, but not unfeasible. Now, there is a system which is very peculiar, but was invented by George Birch, and it's applicable, it's applicable to dilute neutron matter which exists in neutron star crusts. So that's a physical object which is interesting, and I'm going to talk that first. Yes?
Sorry, but
no, sorry.
I'm not fully understanding. When you mean density, you mean density of neutrons, density of protons, you treat them and then you put the isospin?
No, I have separate. I was a little bit flip here because I have the spin density of protons with spin up and spin down. The same thing for neutrons. I have the kinetic energy density for spin up and spin down protons and neutrons. I have the anomalous density, I have spin orbit density, and I have the current density. And I believe this is all of them.
Okay, and second thing, you say that mathematically they are the same when you have one body, but then if you want
No, one body density. Yeah. Because in principle, the Holmberg theorem, Schramm theorem said that all those, you see, so let me go back to that. You see, so what the theorem says, if you know only the number density, you determine the entire function. Now, the fact that I use several densities, not one, that's a simplification which is needed. You see, for example, I don't know how many of you are familiar with the interacting boson model. You see, probably heard about that.
Yes.
And one of the great success there, they introduced S boson, and D bosons, but only D bosons are observable, S bosons are not. They are simply there to conserve particle numbers. But it makes mathematical structure very simple. Okay, you continue. It's the same thing here.
No, my question is because I don't know if you want to describe the fission until the end, but at some point you have a transition to two-body.
You'll see. You'll see what I do.
Okay.
Okay. Okay. So the other thing which is very important in this case, you see, the density function depends on time, and in particular on currents. These ones you might determine from static solution, but in static solution you don't have currents. And the interesting thing is that simple Galilean invariance determines the dependence. You don't have to think anymore. You say simply implement that and it works. And I'll show you what that means. Now I'm going to talk to you about the unitary Fermi gas, what it is. In 1999, he issued a challenge. Find the ground state of a unitary Fermi gas. What is that? It's a system with zero interaction range and infinite scattering length. If you think of neutrons, probably everybody in this room knows the scattering length of 2 neutrons is about 20 Fermi. It's very large. Then the radius of the interaction, it's about 2-3 Fermi. Right? Now, you have an enormous interval between these two quantities. And now George said, let's take the scattering length to infinity and the radius to 0. It's an ideal system. At the moment, it can be created in the lab and is done in hundreds of laboratories. It's studied theoretically, and I'll talk about this. You see, this is the reason. Okay, I'll do that. And basically, you see here he explains, you see the reasons for that. If I have a dilute system, only the cross-section in L equals 0 partial weight it's needed. So you need the scattering length and you need the effective range. This is a formula derived by Bethe in 1936, I believe, or so. Now, the cross-section has this form. And now you see here something very interesting, that if you take the scattering length to infinity, this cross-section becomes infinite. You see, this is a very unusual system. But as I said, it can be created in the lab today, and is done routinely. Let's assume that I look at this system, and I want to calculate the ground state properties of this. The only quantities it depends on, it could be number of fermions I have, the volume I put them in, h bar, Planck's constant, it's a quantum system, the mass of the fermion, and these two parameters. But now if I take one of these to infinity, this to zero, this function depends only on these four parameters. That's exactly like free electron gas. Out of those parameters, there is only one quantity we can make which has dimension of energy, and is this one, where this is the Fermi momentum. And then the total energy of the unitary Fermi gas is the energy of a free Fermi gas times a pure number, like pi. It doesn't have a dimension even. And now the question is, what is that number? Obviously, if the scattering length is negative, you have attraction, so that number should be negative. The energy should be smaller than the free Fermi gas. But could it become negative, that number? If it's negative, sigma, psi, the system collapses to zero volume. If it's positive, it's a gas. And he issued this as a challenge, put out of his pocket $300. That's fine. Another person added another $300, and the person from Los Alamos, George Baker, he provided a solution, won the prize. 2 years later, that was proven experimentally and theoretically. This is the answer. Okay, I'm done. We'll go to the break. Thank you. Any questions? Remaining questions? Yes.
On one slide you show the density function as a sum of waves with one coordinate. At the very bottom.
Yep.
Are we sure there is only one set, or there is plenty of set of phi I that can?
That's a very good question, and actually there is no answer to that. It could be many in principle. And the question is how many you have. That's one of the things which you have to find. But now what you do what you typically do. You choose the simplest possible solution and you see if it works. If it doesn't work, then you start complicating, adding decorations. And this is the route, typical route in science. Yep. Okay, I'm pretty sure there'll be more when I talk about fission. Thank you.
You're going to apply that to fission, right?
I'm sorry?
You're going to apply it to fission.
Absolutely, you see, that's my goal.
Okay, so mini break, and then we come back.
Yeah. You can do quantum Monte Carlo simulation of this system for infinite uniform system because this is the gas. In that case, the density is constant. And the only thing you have to find, you see the value of psi. Actually find something more, that the system is superfluid. Is the superfluid the highest critical temperature ever of any known systems? Now you can put a system in a trap and you can solve the quantum Monte Carlo problem for that. For different number of particles spin up and spin down. And there are something like close to 100 cases already calculated with high precision. And also, you see the time dependent is a bit trickier. But I'll go very fast. You see here it's a comparison between quantum Monte Carlo and the SLDA. The agreement, it's within the statistical errors of quantum Monte Carlo, you see. So we can do better, but at the moment you see we cannot do better because the errors, they are bad. This is one thing which I'm particularly proud. In 2013, there was an experiment done in cold atoms, this unitary Fermi gas. You make a cloud, illuminate on one half with the laser, and then you form a soliton here which travels back and forth. And the result were published in Nature, heavy soliton. The theory will tell you that it's certain frequency going back and forth. they found the frequency 200 times lower. If that would have been true, then probably this would have been very close to a Nobel Prize. We told them this is a vortex ring. A vortex ring, you know, it's a vortex, you know, a tornado, but it's quantized. That's the only thing. And it's vortex because it's a trap. And it fully describes that. They eventually made the experiment and found it's a vortex ring. So I'm not going. So we corrected the experiment, the prediction, and they correct. Quantum turbulence. No, I think I don't need that. This is another thing which we did, which applies to neutron stars. There is a problem known for more than 50 years now, glitches in neutron stars. You know that they rotate, and at some point they accelerate fast, and the question is why. I'm not going to go there. It's the fact that they have quantized vortices and they pin on the crust. We solved the problem in 2013. So now I'm going to go to nuclear fission, because this is my goal. And I'm going to go as fast as I can because I really have more slides than probably I can present. But at least they'll be there for reference. As I said before, my preference is quantum mechanical framework. No assumption, no approximation. If I make an approximation, it has to be controlled. I have to know the error of that. And I do. And I'll argue that I'll need, it's actually 7 parameters because one of them is the proton electric charge. And to be honest, I have to put the average mass of the nucleus, so it'll be 9. With this, we obtain a better description of the entire periodic table of even nuclei than any density functional theory. Maybe with the exception of one. But our is not even optimize the system. So I'm going to stop there. What are the elements, physical elements? Binding energy of symmetric nuclear matter, the density, the surface and symmetry energy, and in particular its density dependence, the proton charge, spin orbit coupling, pairing gap, or pairing strength. These are the only elements which I need in order to describe fission. They are known for decades. So I'm going to use them and see what I can do in nuclear fission. So I can start here, but probably I'm going to jump directly to nuclear fission. You see, typically to tell you that we use a range of supercomputers. And to go a little bit through theory. This is a picture from a paper published in 2020 by about 3 dozen theorists. I wasn't one of them, where they said that the motion outside the fission barrier is dissipative. As I said, if you're on a mountain slope and you don't have skis, you're going to go very slowly down the slope, you see, because you have very strong friction. Until then, you see, basically, everybody ignored that, except in some phenomenological models. Now, what happens if you have that? You don't have a potential energy surface. You have many of them. And how many? You use Bethe formula for the density of levels. At the energy about 7 MeV, it's something like 10 to the 5 energy levels per MeV. You see, experimental fact. So this is how many potential energy surfaces you have. So basically, you're on one of them, move a little bit, there is a nearby another one, and they are going to jump from one to another. And this is the reason which leads to dissipation. Okay, fission. We implemented that on nuclei, and this is what happens. And here, we didn't know exactly what kind of pairing to use, and they used volume pairing, volume and surface pairing, and 20% volume and 30% surface. And here you have neutron density, here you have proton density, so above and below. And here you have the pairing gap in the initial state for the neutrons and for the protons here. And you'll see everything as a function of time, what happens. We started the simulation with that initial condition in 2015, and this is what happens. You see, depending on the value of the parameter, which controls the rate of dissipation, by the way, you see that eventually the nucleus splits into two. It was for the first time when that was obtained, starting at the top of the barrier without any assumption, any approximation, and so on. And I'm going to speed this up, because basically everybody finishes there. So I'm going to go to the next one. Pairing is an essential element. The reason for that is the following. So I'm going to go back to a slide here to show you. This is a picture from a famous paper by Hill and Wheeler. They made the nucleus to be a cube. Well, they didn't do a spherical cow, they did a cube because that was easy. And they started elongating it by preserving the volume. But then the particles go, single particle levels go up and down. And then what they say that if you leave the particle in the original levels, the energy of the nucleus increases like this. But they discovered why at this point not take two particles from here and put them here. And then you go into a different parabola and so on, and take the envelope of that and you obtain the liquid drop formula. And this is a thing which I learned a long time from Migdal, Arkady Migdal. If you have a nucleus and try to stretch it a little bit, you need a lot of force, but if you want to stretch it a lot, the force is much smaller. And this is illustrated here why. Okay? But now, why pairing is important? Each level is double degenerate. So if you come to a level crossing, one particle will jump, but for both of them to jump, because you need both of them to jump, the probability should be considerable. But if it's smaller than one, for two particles, it's p squared, which is much smaller. But if you have pairing, you have a Bose condensate, and then the transmission, the jumping gets enhanced by Bose enhancement factor. This is what Birch discovered a long time ago. And that is essential. Now, this is what I'm going to skip. How good was that description based on a very rudimentary energy density functional? This is plutonium-240. We predicted the neutron number of the heavy fragment, 83.4, and there is an error bar. It's not an error bar. We have statistics because they have different initial conditions, and there's the error bar there. And the charge was 53. Compare with systematics. The systematic is 85. This is 83.4. It's basically less than 3%, if I were to quote, Frederick from yesterday. You see, so this is pretty good. The same thing for neutrons. But what was important, we discovered, we look at the excitation energy of the fragment, and this was absolutely remarkable. We start with a cold nucleus and end up with two fission fragments, and they are both hot. And they have unequal temperatures. And the heavy fragment is cooler. Explain that. They were in contact for a very long time, but the temperature didn't equilibrate. We calculated the TKE. And TKE, here it's what experiment tells you. No, what theory tells you. And the experiment is here. We're basically on top of the number. So for the first attempt, because this was really the first attempt we did, we pressed the button, let's see what it gives. This is what we got. So I'm going to go a little bit further. So pairing is very important. Without pairing, this won't happen. Nuclear collision can help, but unfortunately they are not enhanced. They don't have the Bose enhancement factor, which pairing has. Now there is another thing about pairing which is here, and you have to watch this movie towards the end. Remember I told you that the fission fragments are hot. I'm going to stop the movie here. Oh, let me stop. It's good enough here. You see the pairing gap here, it's not vanishing. And this is 20 MeV, roughly, excitation energy. In no textbook in nuclear physics you'll find that in a static solution, at 20 MeV excitation energy, you have pairing. In a time-dependent approach is there, and it's maintained all the way towards the end. Okay, so this is the element I want you to be aware of. Now, oh, sorry, I didn't see you. You see, I'm trying to face all of you, but I
I
can't.
want to make sure I understand. So you're saying
Yes.
that the fission process is dissipated,
Yes,
and part of that is because there's superfluid motion between the two fragments?
because you jump from one surface to another. You don't stay on the lowest slope.
Mhm.
You see, because there is another slope here, another slope, and actually you pass on these slopes, and the energy basically is constant. So instead, you see, like a train which will go down the slope, will transfer the entire potential energy into kinetic energy. In this case, you block the wheels, and if you let the train go down, the wheels will get hot, but it will move very slowly. That's exactly what happens here. Make sense?
Yeah, where's the energy going?
As I said, the nucleus gets hot. Make sense? That's why it is. Instead of going into kinetic energy, it goes into thermal. Yes?
Then your analogy made me think that there is some friction there.
Yep. You can call it friction, but it's not real friction. But anyway.
Yeah. And when it comes to superfluid,
Well, this is one of the wonders of quantum mechanics. I can spend a lot of time on that, but I don't have the time, unfortunately. But we can talk about that. Okay? Yes.
Quick question. What do you mean by hot and cold specific?
Well, a nucleus at 20, yeah, so at what excitation energy in a typical nucleus pairing energy disappear? It's about 4 or 5 MeV. Now, these nuclei have almost 20 MeV, each fragment, almost 20 MeV. So they're definitely above the critical temperature for the pairing correlation to disappear. But they did not. But there is another fact why they did not there, so I'll go back to that. You see, there are so many details that I cannot cover them. So let me go here. There is a difference between pairing, and here we don't have everything which I want to show you. We have only the magnitude of the pairing gap. I should show you the phase. In a static case, the phase is constant everywhere. Here the phase is not, and the magnitude is not 0. So this is not a regular pairing condensate. But the pairing correlations are there. And basically they simulate collisions, two-body collisions, like in Boltzmann equation. They are absolutely analogous to that. Okay, I have slides about that, but I cannot go in any more details than this, unfortunately. But there is in the slides, there is reference. Yeah, any other questions here? Okay. Here, for example, we calculate, so if you look at this system, you see this is from first FIESTA, by the way. Gonnenwein, it's a famous experimentalist. I don't think he's active anymore. I don't know if he's alive even. You see, do you know? I have no idea. But this is basically the picture of Lise Meitner and Otto Frisch. You don't have a second barrier, you don't have a double hump. And so. It's simply surface energy, Coulomb energy here. They compensate at this point. This is the outer barrier. If you go down, all this energy from here to here, it's converted to kinetic energy. What is this drop here? You see, they have a delta V here somewhere. Do they have it 17? I don't see. It's over there, 17 MeV. We calculated. Look at what we obtained. We obtained 1 MeV. You see the difference? It's enormous. We barely move down the slope. This is what I'm trying to tell you all the time. Okay. Now, you can look at the shape of the fragments and so on, so I'm going to stop about this. I'm not going to talk about that. We went further, and this is another thing which I think we established for the first time theoretically, and I think it has impact now on the phenomenological models. We obtained the fission fragments, but you can look at their properties apart from the temperature, the spins. Now you have a big fragment and you have a small fragment. In all phenomenological approaches, and one of the main authors is sitting here in the front row, the spin of the heavy fragment is proportional to the mass of the heavy fragment at power a to the 2/3. Am I correct, Patrick? I said the spin, in phenomenological codes, until now, the spin of a fragment is proportional to a to the power 2/3, where a is the mass of the fragment. Huh? I'm sorry? It basically that, but if you compare the heavy and the light, heavy is bigger than the light. That's the point. We obtain just the opposite. The light fragment carries more moment. This is the moment of the light fragment, the distribution, depending on variety, and the heavy fragment is this. On average, the average spin of the heavy fragment is smaller than the light fragment. Moreover, we look at the correlation between the two spins. They have spins. What they can do? They can do this, they can do this, they can do this, and they can rotate. And basically, two modes of them, you see, this is bending. You have the two fragments exit like this. They are deformed, so they rotate this way. But there is a mode where they do this. And we find out they are an anti-phase. This is the bending. No, this is the bending here. Okay, and then you have the twisting, because you have one fragment rotates in this direction, the other one rotates in the opposite direction. You have to conserve the total momentum. The initial momentum is very small, of the order of 1. This is of order of 10, each one of them. So they don't add up to 0, both of them, because they are not equal. Where the third goes into relative momentum. And then if you add the 3 of them, you obtain all of them. Now, the other thing which is here, what happens if instead of thermal neutrons, you increase the energy of the neutron, which impacts the nucleus? And we went up to 25 MeV, and we found out that energy of the heavy fragment, excitation energy, increases faster than the energy of the light fragment. You remember initially they had opposites, so the light fragment was hotter, and then the spin of the heavy fragment increases faster, and the light fragment stays almost constant. Anyway, we have those trends, which apparently some experimentalists see it. So I'm going to skip this, and I'm going to go to this. This is a code developed here at Los Alamos, CGMF, Cascade Gamma Multifission or something. The acronym doesn't describe what the code does anymore. You see, the code does much more than that. But in particular, what it does, it predicts the spectrum of the prompt neutrons. But you can study that, and this is the experiment here, and then you can do the simulations when the excitation is that thermal neutrons, so 5 MeV neutrons. And basically, they observe very small differences. But in experiment, the differences are pretty big. We did analysis of that. We included that, what we learned from our simulations. And basically, now we are on top of the experiment. You see, that's simple knowledge which we learned from theory. Now, the last thing here, you see, and I'm going to make a parallel here. Think of the two black holes. You know, they collide and they collapse and something happens. They orbit against each other for millions of years, and then for a few seconds they come very close to each other. In a fraction of a second they collapse, and then you hear that beep, which became famous, for which they got the Nobel Prize. That beep has a frequency of 200 to 300 hertz. And it lasts about a fraction of a second, half a second. You see, this is what it is. This is the equivalent in reverse, what happens at scission. So I have the nucleus very slowly evolving towards scission. I think I convinced you of that. And at one point you form a neck. And this neck, it's ruptured. And this is absolutely, it's an element as dramatic as in the case of collision of two black holes. Black holes spend a lot of time doing nothing. If they rotate like this, but in less than a second they collapse, and you get a Nobel Prize for that. well, in this case, I don't think we'll get a Nobel Prize for that. But, but what happens, you see, the process when the neck ruptures, it's very fast. How fast is it? It's less than 50 Fermi over C. What is 50 Fermi over C? The time it takes a nucleon to go from one end of the nucleus to the other and come back. This is how fast this process is. So the nucleus ruptures extremely fast. How long it takes to get from here to here? It's about 1,000 Fermi, 2,000 Fermi over C. I have the time scales, we calculated those. Unfortunately, those probably nobody will be able to measure. Like this, also, you won't be able to measure directly. Like you cannot measure directly what happens with two black holes when they collapse. But you hear the sound. And we tell you what is the significance of this sound, and you might see it in experiment. When they start separating, at the beginning, you have two clouds forming here on the axis perpendicular to the fission of axis. And if you look, we have a movie of this, and Ibrahim is going to talk more about this tonight, or this afternoon. This, what happened to the neck here, the information is passed on to the other end of the nucleus, and you have something else emerging here later than there. And then you form basically three clouds, you see, which is in this plane and in this direction. And they are very distinct from prompt neutron fission. The average energy per neutron is about 3 MeV, which is significantly higher. And they have a distribution which is basically isotropic, because the prompt fission are emitted from moving fragments, which are moving pretty fast. These are basically at rest. They basically didn't have time to do anything. Anyway, so this is the insight you can get. Another thing which we did relatively recently, we did induced fission of odd mass and odd nuclei. And we have so far something 113 trajectories. We did plutonium-241, plutonium-233, uranium-239, and neptunium-238, which is, these are the compound nuclei. Yes?
What are the clouds?
I'm sorry?
What are the clouds?
The sounds?
The clouds.
Oh, it's the neutrons.
Neutrons.
Neutrons, fission neutrons. So when you rupture like this, imagine they have a liquid drop. You see, drops on the floor. You have little drops coming out. It's the same thing, qualitatively. But in these cases, it's mostly neutrons. Sorry, I wasn't explicit. Not many. The total number, if I remember, it's per fission event 0.3. But they carry a lot of energy.
So experimentally there will not be...
You see, there is a... So let me make a small comment here. They were predicted by Hill and by Bohr and Wheeler in 1939. People look for 50 years, and there is a famous book edited by Wagemans, 50 years later. In the introduction, he says, they don't exist, both theory and the experiment. And until now, people are still arguing. One author of that argument is sitting here, there, you see, and we argue with him a lot. So this is the best we can do. Whether it's true or not, it's up to the experiment to prove. So we make a very distinctive, you see, very clear prediction. Find it. You see, like collapse of two black holes. Find it. Okay. So now about this, I'll be relatively... How much time do I have?
15 minutes, I think. Yes.
Okay, so I'll go a little bit slower than here.
Time for questions, more questions.
Yeah, that's fine. Yeah, but maybe I'll conclude faster. This is a very tricky topic for theorists, and it goes back, you see, to this picture. Imagine that on one of these levels, I have not two fermions, I have only one of them. Pairing is not going to help, because pairing needs two of them in order for them to jump. And what will happen to that? He will be on this level, it will go higher, it will go higher, it will keep going higher, and the nucleus won't like to fission. At least this is the naive expectation we all have. The thing is, nobody did the calculation of that because nobody did the real-time calculation. This is the initial state, follow it in time, find out what will happen. We did it. But there is another calculation. You see several people in the audience, so you see I'm going to talk about them, did that. But I have an opinion about that. So this is one thing. The other complication is, once you have a single nucleon sitting up there, it carries angular momentum. That's a vector, but it's a pseudo-vector. It has p parity 0, t parity -1, or 1, whatever you say. So it's p even, t odd. And that's a preferential direction in the system, which is going to influence the distribution of matter. You might say it's only one of them, but it's near the Fermi surface where the levels are very dense, so the influence is going to be major. Now, if you look at the spectrum of excitation of for example, even nucleus, you see there is a big gap. This is the pairing gap here. Actually, the pairing gap is here. You see, from here to here, it's about 2 MeV, because this is a rotational state. It's an excited state, a different momentum. But if you look at the neighboring nuclei, you have many levels there, which are multiple degenerate because they have a finite angular momentum. If, for example, you see in this case, you have here somewhere something like 11 halves, that's 12 times degenerate level. So if you look into a small interval less than 1 MeV, you have several dozens of levels. You see, so the spectrum, so the nucleus that is relatively easy to deform because of that, doesn't require much energy. So what do you expect, for example, experimentally? And this is a systematic from a wonderful book written in 1973. I still read it, lots of things to learn from that. And I suggest you really have a look at it. Here you have the spontaneous lifetimes, half-lifetimes, of even nuclei with black dots, and this is with odd number of neutrons. And you see the difference here. This is the logarithmic scale here, log of 10. You have 4 orders of magnitude difference. So the fission of an odd nucleus, it's really serious in that. Why? How? How are you going to explain this? Now, if you look at other parameters, for example, you compute the fission barriers, and you have even system and odd system. They're basically the same. So it's not the height of the fission barrier. Right? You might think moment of inertia, well, it's about the same system. You see, one nucleon, it's 1% difference. Shouldn't be much. Nevertheless, you see, it's humongous difference. The other difference is, for an even nucleus, you need the density, protons, neutrons, spin up, spin down, kinetic, and so on. But for odd nucleus, you need the spin density, and that's a vector. And you need for protons and neutrons. And you need a few others. So you need something like 3 times more densities in order to construct the corresponding density function. So density function is much more difficult to do in that case. So what are you going to do? Now, what we did, we created, so I'm going in the wrong direction here. So this is how you do this description. You use either Hartree-Fock or Hartree-Fock-Bogolyov or BCS, you can call. This is the theory of that. You see, I'm not going to talk about that. If you have an odd system in the probability distribution, which is continuous, you make a hole here, or you add an extra particle here, this is what you do. And this is the one which causes trouble, you see. And what people do typically do in this case, there is a procedure called, because that one cannot participate in jumping from level to level, people simply block that system. And that's called Pauli blocking. And how you do that, the ground state wave function is not that, but it has an extra quasi-particle here. You see, all this contain even number of quasi-particles, but because of this contains an odd number. So the parity of this, number parity, it's -1, while for an odd, even system, it's +1. So they're simply different wave function, different system, different quantum numbers. Now, how you can create this state? Oh, there is a very simple prescription. You take this Bogoliubov-Valatin transformation, and you have the corresponding U and V matrices, and single out one level, and then for that one level, you replace the corresponding U with the corresponding V. You see, you swap these two elements, basically, for that level. This is what you do. And then you obtain exactly, you see, this type of wave function. Okay? Now, this is the thing which, you see, I think at least 3-4 people, I think that maybe 4 people are here, you see, at this meeting who contributed to this paper. There is actually another paper which I think is the most recent microscopic attempt how to do this. What they did actually, it was a bit of a cheat. And the cheat was the following. It's called equal filling approximation. You see, this is what EFA stands for. So instead of replacing one V with one U, they did that for the both levels with spin up and spin down. But then now the system, it's not really odd because you have both levels, you see, with particle, that's fine, thank you. You see, unoccupied. And then, for example, if you look at the barrier, fission barriers, they're very similar. This, in a way, it's in agreement with what we know from here. Okay. But this is not really an odd system. It's not odd, it's time even. So instead of that, we simply created a really odd system, started it, and look what happened. Initial odd state had probability 1, as you're expecting Pauli blocking. But we followed the state in time, it didn't stay there. Pairing actually influences that because it depends on time. It's not the same pairing which was initially. So it's a bit more complicated, but I'm going to be a little bit qualitative here. And pairing, it's violated. Absolutely. Now, to do this, you see, to understand what it is, so we did so many trajectories. I think altogether 113 trajectories we did, I think I said here at some point. So we did those. Each one of them required the solution of 864,000 PDEs, coupled, and so on. And we have time reversal symmetry explicitly broken, no approximation. And we look at the fragment properties, TKE, TXC, and find out that they're very similar to what you'll obtain for even system. And apparently this is what in most experiments people find. And the other thing we found, depending on which quasi-particle we excite, however, the fission time can be affected significantly. If we take a very low quasi-particle, so you remember here we have different quasi-particles, they have quasi-particle energy. They can be very low, or they can be high. So we take high, that will correspond to a relative excitation of the system, like 5 MeV or so. If the excitation of the system is low, the system, it takes a long time. But if you follow this on the Q2Q plane, you'll see why. The trajectory becomes at one point very convoluted. So because the potential energy surface, you see, it's not one, but there are many of them intersecting. It's very bumpy. And the system basically is like, I don't know, like an obstacle course. You see, you try to go in this direction, there's a tree. No, you go this way. No, you bounce back and go there. And this is what happens. You go in many directions, and eventually you get out. But if the energy is high enough, these obstacles don't count anymore. So with this, probably I'm not going to do anything more. I'm going to stop here, and I'll be open for any other questions, clarifying questions you have. As you can see here, it's about 2/3 through my talk, so I have more, but you'll have them as reference if you need to. Thank you. Yep. Okay, you rule.
Can you elaborate a bit on the non-Markovian aspect?
Yeah. Markovian means basically that you have no memory, like in Brownian motion. But if you allow for colored noise instead of the white noise in Langevin equation, Langevin equation has white noise, if you remember what it is. You have stochastic, at each time it's a random number. But you create that correlated with what happened a little bit before, then you obtain a non-Markovian behavior. And this is typically, so you know what happened before, because for Brownian motion, you simply specify the initial condition and follow. You don't care what was in the past. Now the question in this case, nuclear fission, does it care? The reason what you see that, you see many people talk about these jumps from one cross level to another. And it takes time. Now the question, how long? And they found out that it's a very long time. In that long time, actually, a few other transitions occur. So all those jumps are correlated. They are not uncorrelated. So it's already implemented into formulas, which looks Markovian from the beginning because you specify the initial condition. But then you follow it and look at the structure, what's happening underneath, and you find out it's not. So basically, this is what it is. Yeah.
For me, it wasn't that clear because you were talking about trajectories and so on. So for the DFT, you first solve static to get the potential in the surface, or you directly start from all the nucleons having a wave function and you just...
You're talking about even or odd? Which one? Pick one. Even. Yeah, so what we do, you saw this potential energy surface everybody draw, you see, so far.
Can you calculate that also?
We can calculate and we have plots of that. You see, but I didn't show them. But now we didn't start, so in principle what I should have done, you see, in theory, but that's still difficult, so let me go, you see, to a thing, you see, which will be closer to that. And that will be clear. Oh no. Oh, I think I have to go much further and then I'll have a slide like that. Oh. Oh, I don't know what. Yeah, here, look at this. This is the Q2, Q3 place, you see, surface. The ground state is here. So basically, when you absorb a neutron, you form a compound nucleus with the next station energy 6 MeV, 6 MeV roughly. And you start from there, and basically you have to think, you see, how the potential energy surface looks. Forget about whether it's real or not. It goes up, goes down, it goes up again, and then it goes down all the way. We start at the top of the barrier. The reason is very simple, and you look in Gonavine lecture. How long it takes a neutron to go from the ground state to the outer barrier? It's something like 10 to the minus 15 seconds. I might be wrong, you see, by an order of magnitude there. Our entire fission process is 10 to minus 20. So we lack 5 orders of magnitude in time to start there. So for that reason, we start at a very late stage where the nucleus is cold. So for that particular shape, you see, which is, you see, elongated like this, we calculate the ground state, and then in the neighborhood of the ground state, we start the simulation.
And when you say trajectory, you mean a specific initial?
That's the initial condition.
Okay.
That's the initial condition. But then I have many of them, so those are different trajectories.
Okay. And, oh.
We'll go to a couple of questions quickly, and then you can. Sorry, but we're running out of time.
So it seems like there's a lot of very impressive results of like total kinetic energy, temperatures, mass distributions, whatever. Were these all achieved like one at a time, where you go?
No, they all obtain the same thing.
Put everything in,
Yeah,
you
yeah.
run it, and
Yep,
it all
exactly.
falls out?
Yeah, we simply specify those initial parameters of DFT, find the initial condition, and simply run it. But at the beginning, we didn't look at everything. But then it's like, oh, we can look at this, we can look at that. Okay, let's through.
I'm impressed.
Yeah, thank you.
So, pretty different question. I was talking to Gregory Patel, who's a fan of the nuclear Josephine effect. And I was wondering, do you think if that's real, would you see it in fission, or the fact it's
Once again, what effect?
the nuclear Josephine effect? So
Josephson,
Josephson, sorry.
not Josephine.
Sorry.
Josephine was a cabaret dancer right in Paris, I believe. Josephine Baker, I don't remember the name.
Josephine Baker.
Huh? Right? No,
Josephine Baker.
yeah, I think. Just an effect. I don't have an opinion yet. It could be, but many people try to discuss that, but they construct models and go from there. And then I said, if you have enough parameters, you see the elephant will wiggle his trunk. So I prefer an approach with no parameters, free, like what I do. And I control everything. So I have a colleague, you see, which participated in the first project, Piotr Magierski. And he's somewhat interested in that, but I don't remember if he looked at nuclei. But he looked at cold atoms, and he saw something like this. Cold atoms behave somewhat similar to nuclei. So if it's there, probably it's here too. But this is the best I can tell you.
And one last question.
Yeah, so all of this looks really impressive. Have you applied this to the sublet region?
Two?
Sublet?
Not yet.
What do you mean?
No, you see, you see at the moment 4 of us, me, Jonel Stetke sitting there. You see, there is my graduate student here. You see, and there is my former graduate student, the postdoc here. You see, the 4 of us, we simply don't have the manpower. You see, in principle, it can be done. And you see the results I showed you on odd nuclei were done during half a year or so. So in principle, we can go there and do simulation anywhere. You see, there is nothing. And we'll obtain something. To what extent will be according to the... We don't have the best functional. You see, this is one thing to say. It's qualitatively good, but it can be better. This is exactly like the Hamiltonian, you see, for nuclear-nuclear interaction. It's qualitatively good, but it's not perfect. So people are trying to make it perfect. You see, we didn't do that. We didn't have time. That's a separate job. We say, good enough. Let's see what it does. Okay? Yeah.
We have to cut it at that, but let's thank our speaker again.
Thank you.